Okay, so this is the first episode of 20 papers in 100 minutes. I will focus on language grounding papers, and here's the folder where 20 papers are stored right now. I will start with some overview papers first and then go over some papers that I found interesting generally. And as you can, for example, see here on the bottom, attention is all you need, which is not a grounding paper, so some general papers as well. Disclaimer, some of them I have already read or looked at like 1 or 2 years ago, so my memories are, there's some memory, but it might be weak. Yeah. Also, I will try to, at some point, make some funny comments, not just keep it super dry. And I will also, of course, not be able to cover everything, so I will try to get the gist of the paper, but then also try to like just point out a few interesting things that might not be like all the interesting things this paper had. And it is, like I mentioned already in the introduction video, it's subjective to what I feel is interesting to my future work or my current interests. So it's not necessarily the objective collection of interesting facts about this paper. Okay, so I will just make myself mentally ready now. Each time I will now start the timer and try to go over the paper. And when I see that the timer hits like a number that's divisible by 5, so 5, 10, 15, I will try to get to the next one as quickly as possible. When I hit 100, I should roughly stop. Okay, and I hope my iPad is able to record 100 minutes, otherwise I have to split it up. 3, 2, 1, let's go. Okay, so this one is what you would call a position paper, and it sort of sets the scene. I wanted to start with a position paper or some position papers. It's called Experience Grounds Language. This is the paper that inspired me to go into language grounding and also pursue a PhD hopefully soon on it. It was written by Jonathan Bisk from Carnegie Mellon, Ari Holtzman, a PhD student at University of Washington, and Jesse Thomason, a assistant professor soon at USC. And a bunch of other very cool and important people, like Joshua Bendrio, quite famous, Mirella Lapata from Edinburgh, quite interesting. Yeah. Okay, so like I said, this is a position paper, and the main position is that, as we can see here in the abstract, this shared experience is what makes utterances meaningful. So meaning gets its language because we have this shared experience of the world. And currently, as they say, today's systems fail that because they can't relate language to the actual physical world. Yes, this is the abstract. There's nothing more like interesting or nothing I will mention later on. And the big idea of this paper, or not the big idea, but they are sort of how they want to frame it and sort of frame our future research is this idea of world scopes. So how much sort of like semantics are available to the model. And they say like there's world scope 1, which is just like very well-defined corpora, like say this is world scope 1 here, the pen tree bank. So this is annotated, it's sort of curated, it's still quite small. This is the beginning of computational linguistics back in the days. Yeah. Then the world scope 2 is when we get just more data and it's less like, it's more chaotic. Here they also talk about like where they still fail. Like here we see a bunch of like typical models that are trained on like a lot of data, like GPT-2 is mentioned here. Lambda is a dataset where models still failed, I think. Yeah. Okay, and then there's world scope 3, which is seeing. So you have vision, and you might even like hear stuff, and they give some intuition why this is important. Wait. yeah, they give you like heuristics, like the certain metaphors, or generally like what language describes is easier if you know what it talks about. Here they also cite an interesting sort of like, they generally cite a lot of CompGuessWhat papers. Okay, I have 1.5 more minutes. I have to hurry up. For example, Hanard is a CompGuessWhat paper, cognitive science paper. They, for each role scope, they also cite like a ton of work being done. Yeah. Oh, and here they also have this idea of like that you can never understand what a painting is and what it all involves, like that there are dirty objects and colors, and that the splash can trip, and like how you would paint something. Yeah. Okay, World Scope 4 now, we have a body, we are in some environment, so we can move around. This often like entails that you use maybe some reinforcement learning. Vision and language navigation is a typical task here. Okay, I don't have much time yet. Blah, blah, blah. Then the next part is that you also are sort of grounded in the social world. You interact with others. There's a theory of mind. You know that language does something in the world. You can make people do something when you say something. You know that others like have a mind like yours as well, and that lets you infer certain things when they say, like, you know, okay, they said this because they probably thought I thought, etc. Sort of meta stuff. Then they come to the conclusion. And here there's a part that also inspired me a lot about persistency, that you need persistent agents. Yeah. Okay, that was the first paper. I realized this is quite a challenging task, but let's move on. Next paper. This one I know less. Also position paper. It's called Climbing Towards NLU on Meaning, Form, and Understanding in the Age of Data, from Emily Bender and Alexander Koller. They sort of are quite critical when people, they have a few comments, I think, and they already say here, like, they don't like when people use words like understanding very, just throw them around. They say we should be careful using such words as understanding or meaning. Yeah, here they say, like they call out this hype of understanding. Then they try to define meaning. So this paper is less about like concrete applications of language grounding, or like this is different than the previous paper because it more tries to answer the question what is meaning, and sort of the difference between form and meaning. And GPT-3 only sees form but not meaning. And they say meaning always has communicative intent. So there's always a purpose for what we use language. They also define language as think more formally as like a pair of expressions and communicative intents, or it's a subset of this. Yeah. Okay, more stuff. Yeah, then the famous octopus test. This has been like cited or mentioned a lot. Where they say you have like two people that communicate from one island to the other, and there's an octopus basically listening in. He somehow like managed to open up the cable and hear what they say. And then he tries to mimic, I think, one party because he listened to one of them a lot, but in the end he fails because he is not actually there and can't see what they saw, etc. Yeah, this is a hyper-intelligent deep sea octopus. Yeah, he listens in on their conversations here. Listens in on their conversations. Very good at detecting statistical patterns, so that's a typical language model. Sort of, they try to have an analogy here. Okay, here comes the point. He feels lonely, so he cuts the cable and wants to speak as well. Okay, and here comes the point where they say it will fail. For example, if we see a coconut catapult, and then person A is the one that actually still talks, whereas person B was now replaced with the octopus, and person B is asked for like suggestions or ideas. And then they say like he can't do it. This octopus, it can't do it because it has never seen such things and can't thinking that way here. Okay, here they have an interesting analogy also with learning about code. Okay, here it is about like that they might learn about the right sort of form, like the syntax, but not the semantics of what the program that's executed should actually do. Okay, I still have 1.5 more minutes. Okay, interesting. They also talk about human language acquisition. This is something I'm also interested about in my PhD, maybe. Let's see what they say. One common reason for believing language models might be learning meaning. It's a claim that human children can acquire language just by listening to it. Not supported by scholarly work. Yeah, it's grounded in the physical world, but also in the interaction with other people. So there's like world scope 5 from the previous paper, social interactions. Here, interesting. Note in passing, it's not that Dutch-speaking kids who watch show by choice nonetheless don't learn German. Okay, interesting. Distributional semantics have long been aware that grounding distributions in the real world. Okay, so this is something I might look into more. This seems interesting. I have 1.5 more minutes. 30 more seconds. This sounds also interesting. I think I should look into this more. Damn. Here they talk about like where should the field now go, and they say like there are apparently top down and bottom up things we could do, and then they also have counter arguments. Conclusion. Yeah, they just say again like bird does not learn meaning, just form, and then they say like what should the research community do? Okay, I'm at 10 minutes now. This will be a paper I will not be able to cover fully. This is a paper that was cited in Experience Grounds Language. It's called the Symbol Grounding Problem. And it's sort of the philosophical or cognitive science paper to cite if you want to write about language grounding. And this is hard. I tried to read it at some point, I think, and I didn't understand too much of the terminology. And here they just ask the general questions, like if you have any symbols, how can you maybe just let me read it out loud. That's the summary of his thing. How can the semantic interpretation of a formal symbol system be made intrinsic to the system rather than just parasitic on the meanings in our heads? So what he means is that only when we see the symbols, like the system is juggling around symbols and producing some output, but only when we interpret the symbols through our grounding we already had as a child, for example, then it gets meaning, and it's not intrinsic to the system itself. How can the meanings of the meaningless symbol tokens manipulated solely on the basis of their arbitrary shapes be grounded in anything but other meaningless symbols? So this is the problem if you have some foreign language. You can't get the meaning of a word by just looking up the definition of it in the lexicon and then looking up the definition of words that were used in the definition. This is just circular. The Chinese room argument is also similar. Like the problem there is that it's also not grounded probably. And then he says like they must be grounded in two ways, bottom up. The first one is iconic representations, which are analogs of proximal sensory projection of distal objects and events. I think I remember looking up distal, but I forgot what it means. And categorical representations, which are learned and innate feature detectors that pick up out the invariant features of object and event categories from their sensory projections. Let's see if we can find out at least in the 5 minutes what the difference between those is again. Here he defines what a symbol system is. Set of arbitrary physical tokens that can be manipulated with rules. You have to interpret them. Some semantic theory or function. Connectionist system. So now he goes into like AI a bit, cites like the typical McClelland-Rumelhart stuff. The Chinese room argument. But I want to know, hopefully I can still do this in just 2 minutes. Here. iconic and categorical representation. Depending on our forming iconic representations of them. These are internal analog transforms of the projection of this level. I think this is probably not defined here, but maybe. Okay, I can't even click it. I hope I can still figure this out in 5 minutes, otherwise we have to move on. Iconic representations, that's the first one. According to the model. But what are icons? Is it like an exemplar theory? Symbolic representations. Category representation. Okay, categorical. Maybe the second one, symbolic representation, is just like sort of splitting it up into like how to define it. Like zebra is a horse in stripes. Okay, zebra has the grounding through its grounded symbolic representation. So iconic is the typical one we would imagine like being grounded in some pixels or exemplars. Conclusion, shape of the iconic, blah blah blah. But now my time is up, and I have to move on. This is the first paper I have never looked before at. It's from Robots That Use Language. So the idea that robotics needs language because it might get instructions from a human and stuff. And this is very tricky still, and also very tedious to work on. This is an overview paper or a survey paper from Stephanie Telex, an expert on Robo NLP, robotic language sort of stuff. So let's see. I think here they define grounded language understanding, interpreting a natural language utterance in terms of the physical state of the robot and the environment. Okay, so this is sort of like grounded language understanding. You understand a word subjectively to what your state right now is in the world, and in what environment you are. Okay. I think here is most useful to, instead of like reading the introduction now, they would probably say like why it's important to provide natural simple ways for people to interact with and control robots, give instructions, etc. So that's the motivation. Here we see some humans communicating with them. Figure 2 shows a flow diagram for language using robot. Okay, you get the language input, blah, blah, blah. Grounding. Here happens the grounding, okay. Perception. You see something, you maybe parse it into some, like, it gets through a CNN or something. You connect it with the language, maybe with some, like, simple multimodal bird or whatever. And then, based on that, you may have to take actions. And maybe also describe what you did, maybe. Then I guess they say what grounded language is here in that part. Language that refers to as interpreted in reference to the physical world. Okay, that's a neat definition. That's similar to how I normally describe it. I like that. I always thought about, like, I guess you always think about examples of, like, when you try to explain why it's important, you always get examples, but it's nice to, like, sort of collect them. I was already thinking about, like, making a long connection of things, like 100 examples of stuff. That is a good example of why we need grounding. Interesting. They go into syntax. Have been created a structure. I wonder if that is connected to language somewhere. Now they just say language is compositional and has a, like, very intricate structure. There's also formal semantics, but I don't have much time left. Okay, we cluster approach based on 3 basic grounded machine learning methods. and HRI-centered approach. So now there comes the part that is typical for a survey paper. You try to classify methods or certain trends in research into parts. So they say cluster approaches into lexically grounded methods, learning methods, and human-robot interaction-centered approaches. The first category, lexically grounded methods, focuses on defining word meanings in a symbol system, typically through a manual or knowledge-based grounding process, and using logics, grammars, and other linguistic structures to understand and generate sentences. So, yeah, I guess they say like you have the typical sort of NLP pipeline in some way, like logics, grammars, and you have some grounding into like vision. I don't know why they say, like in the second one, they just say like the second category covers learning word and utterance meanings from large data sets with inspirations drawn from machine learning and computational linguistics. The second one just sounds like bird would fit into that category, right? And the third one is about how also focus on the language experience for people interacting with robots. So this is also about maybe almost psychology research in some way. And also what language maybe use, simpler language with robots, such research maybe. Okay, lexically grounding tokens. Okay, my time is almost up. Cognitive architecture is interesting, okay. Yeah, I recently read a book where they also use grounding on cognitive architectures. Formal reasoning, 6 more seconds. I didn't get through it. Okay, here I guess are the things we currently see a lot. Oh, this sounds interesting. You are using robot-supported language learning. This one's also like an interesting figure. I like this paper a lot, but now we have to move on. I'm already a few seconds behind. This is the last one. The last, I think, survey paper I have here. It's from a single author, David Schlangen. He works a lot on like grounding, but also not just grounding, but like language games, as it says, or like the interactive part. And this is again similar to Bender's and Collar's paper, one that critiques current trends in research. Here he cites two typical sentences or like motivations you find in papers, where a lot of people just define a new task and say this is our contribution, or then others take this task and we improved it by some number. What he says is like people just assume this is progress, and nobody really knows what it, or like people just implicitly think like don't know what the progress is towards. Here we make more precise than normally impressionistically induced notion of language task and language game and ask how a research program built on these might make progress towards the goal of modeling. Okay, tasks. I feel like it's quite hard to, like, such a sort of position paper to read it in 5 minutes. Here he defines tasks. So this is, I guess, the typical one where you just say you have input and output, and the task is yeah. He says like the actual task is often just informally described what the task is, like translate something. Yeah, the task is specified extensionally through the provision of a data set or examples of the mapping. So you don't bother defining the task, like what precisely does it mean to translate, but you just say translating means like doing what those 1 million examples here do. And this covers almost all of natural language processing. Here he gives translation. Understanding task, where the mapping requires demonstration of sensitivity to language meaning. Okay, worlds. The language comprehension plays out and repeat a task, not single step ones as described in the previous section. I guess the most important part here is games though. Maybe let's look at that in the short time we have. An interaction game is a setting where players can produce actions. A privilege, but there's sort of nature of the environment. Again, we assume that there's an informal game description of a language game is an interaction game that embeds language tasks. So the tasks are part of such a game. For example, one player asking the other player answering questions would be a language game that poses repeated language tasks to the players. So there's more of a notion of like memory and like keeping track of what the other like player did and stuff like that. Here it is. Game G is in an environment and involves tasks. And a dataset exemplifies this game. What makes a good task build game? I'm afraid we won't see what makes for an interesting language game. That sounds like an interesting question here. Okay, one more minute. Let's find it out. First, we note that games seem to be less well exemplified by this. Here he says like it's harder to sort of just say the game is what the dataset says the game is. So it's harder to just implicitly define the task by just having a dataset. Yeah, and the output, so it's harder to define, for example, also because the output can be a sequence of actions rather than a simple one. Like, there could be like a 5-step sort of thing that you can't put in the dataset. And the language navigation task, while the input is a single datum, a verbal description of a collocation, the output is a sequence of navigation actions. As the site for making progress. Research is an incremental enterprise and new data environment games are interested in a concept. You can now distinguish several modes of making progress. Better models, better datasets, better task and games. This sounds good. And my time is up, unfortunately. Conclusion, making it explicit. Discussion above has more normative. It will closely be the most frequent way of contributing to the project is by improving models. Here. He says the most frequent way is this, but I guess he says more explicit about assumed advantages and how they connect to the goal of modeling language competency would be helpful. So less worrying about like improving models, but more improving like our understanding of making it implicit. And I'm already over time. Okay, this is a hard one because I'm not an expert in cognitive science, and this is a CompGuessWhat paper to some extent, I think, towards embodied language understanding. I want to go into cognitive science at some point, so let's see. Or like learn a bit about cognitive science. Embodied cognitive linguistics. This sounds something I want to look up at some point. Today's technology differs from human like. So here they say like this typical problem like humans need way less data, inferior efficiency, interpretability, and generalization. We're very bad still. This work proposes an approach to represent and learning based on the tenets of according to a natural language is inherently executable, like programming languages. So the idea is here that natural language always does something in the world, like inherently. Driven by mental simulation, metaphoric mappings over hierarchical composition of structures and schematal lens for embodied interaction. I'm not sure if 5 minutes are a good way to read a CompGuessWhat paper. This position paper argues that the use of grounding by metaphoric inference simulation will greatly benefit NLU system and propose a system actually along with a roadmap towards realizing this vision. So I think they will propose some like framework, but not the actual like code or the actual model. Metaphoric inference sounds interesting. And simulation also. So this sounds like some big like cognitive science AI goals. Let's see. Open domain challenge or build with boxes, creates and objects. Metaphoric inference capabilities essential to knowledge representation. General language. This sounds like an important sentence here. This position paper argues that executable semantic parsing and grounded approaches to NLU constitute a first step in a much larger program whose outline is set forth for general language understanding through ECL. Posits that execution simulation is a part of semantics essential for addressing some of the persistent difficulties in text understanding. Our contributions are we analyze inherent in the limitation of state-of-the-art. bring together ideas from CogSci, AI, NLU. I just want to, before the time ends, just want to see what he means by metaphoric inference. Metaphoric inference, the process by which new information might be inferred by structural similarities to a better understood instantiated system. For example, I have an example in mind, suggests that the abstract concept mind is mapped to the more concrete domain of containers. Okay, this is quite interesting, and it has to do a lot, I guess, with like, yeah, being embodied and like, yeah, this is quite tricky. This is something to think about. So, but this is the idea, metaphoric inference, to see this, and then you infer that the mind must be similar to containers. So this is the inference part. Concept, primitive, let's look at that. Neural natural language is a neural programming language, conceptualization. Okay. Proposal for an embodied language understanding, formal framework. Following the view. So this is the model that they suggest, like, yeah. Consciousness prior is a framework to represent the mental model of a single event through the notion of abstract state representation. See an abstract state correspond with... okay, this is hard to read if you haven't read the literature. We adapt CP to a two-player cooperative linguistic communication setting. So here it is about like this typical notion of like that you have a language about cooperation and stuff. But now my time is over. Some more stuff. I guess like theory of mind, mental model of the other person, blah blah blah, agent. Ooh, more stuff. Okay. A bit behind. Okay, now comes the first paper that's not a position paper. ALFRED. So ALFRED is a benchmark for interpreting grounded instructions for everyday tasks. It's from a bunch of people, mostly I think from University of Washington or AI2 Allen Institute. And the idea is they propose sort of give us an environment with a lot of annotations. So this environment, what is it? Let's see, what is it based on? What is the sort of like just the visual stuff, or like I don't know where the kitchen comes from or what sort of engine is behind it, but the idea is that they annotated 25,000 language directives corresponding to expert demonstration of household tasks. So you had people sort of I don't know if the instructions, I guess the instructions come from one annotator and the execution from another, but the general idea is you have this instruction, and then as you can see, you have someone sets the goal. This is a high level goal, and it consists of lower level instructions, and those were all provided. The instructions, the goal, and the execution is all provided by human annotators, and you have 25,000 of them. And here the sort of hard part is to know, for example, at what point am I done with this? Like sort of checking the box, ticking off the box when you're done with it, and keeping track of what you have done so far. And if you only see the goal, for example, and not the lower level task, like inferring that this high level goal consists of those things. Egocentric vision, this is always like a big sort of question. Is it egocentric, or how much can you see? Are you like an omnipotent being, or like humans with two eyes, sort of? They are the typical motivation, blah, blah, blah. We need grounding. We've seen this a lot today already. Like here, they compare to a lot of other environments, Metaport 3D, AI Thor, AI Habitat, and they say we are better. ALFRED, it's in English, of course. Average 15 steps each, resulting, so as we can see here, T50 you needed a lot of steps, and I guess one step is, for example, like one action could be like going 10 centimeters forward or moving your arm. I don't know exactly what the steps are. Localization suite is a soft. They say in our cases localization is not treated as a solved problem. I think you later on see that for them localization means that you have to predict a mask, and if that mask overlaps with you predict this mask, and if this mask overlaps a lot with the cup you want to get, then you got the object right and you can pick it up, sort of. Here they compare it to a lot of other data sets. And here's ALFRED. It has a lot of examples, more than all others. Granularity, I don't know exactly what that is. High visual quality. Egocentric vision, so that you don't see a lot of stuff. At least it's not a graph, so graph is quite simple. Like you can just walk from like each room to the other rooms, whereas discrete, I guess, is like a grid, and at least like you can inside the kitchen have different positions to walk at. Okay. You have, I think for... Okay, there are another example, the ALFRED datasets, export demonstration language baseline. Then they show their baseline models, and we already know that they failed. Like from Jonathan, you hear a lot that the baseline didn't work. Here they describe it. So you have a ResNet to get the visual features. You have an LSTM to process the instructions, and my time is almost over. And then we can see they're quite bad scores. Conclusion. Well, this one is right. The long horizon of ALFRED task poses a significant challenge with sub-problems including visual semantic navigation. These challenges may be approached by models that exploit hierarchy, so sort of splitting up tasks into other tasks and into other tasks again. Structured reasoning and planning. I don't know what exactly that would entail. I guess we have to look at the citation. Yeah, time is over. Interesting. So this is like the general idea. They provide a new way, or like a new benchmark, a new environment to test stuff. Now we got to attention is all you need. This is the paper that introduced transformers for the first time. We propose a new simple architecture of the transformer. So this is just a classic paper I wanted to sort of include here, that it doesn't get too boring. They show this, it is generally about solving machine translation, and showing a new architecture. Here they sort of say like why it's better, because before we used LSTMs, and LSTMs inherently can't be parallelized, and they also say that they say here attention mechanisms are good because you can model any kind of dependencies, even long-term dependencies, and it's not like you don't have this vanishing gradient problem when you have to remember something from 100 precisions ago. Yeah, and they're the first that like completely discard any like recurrence. Yeah, follows this overall using a self-supervised. Yeah, so just the famous picture we've seen before. You have the encoder and the decoder. You have attention in between, and attention. The most important idea is here. I guess the idea is that you have contextual embeddings for each word. You want contextual embeddings, and you get this that it be by in each layer, letting the model look at all other words and then building some contextual representation of the words. Sort of as an example, you have Q. This is like some word would say I have a query because I want to have a better contextual representation, and I encode that query or what I want to know to get a better representation. I encode it in this vector, and then the other words can give keys, what they sort of can show. This is all very metaphorical right now, I know. And then you can see how good they match, and the query says, cool, you have the stuff I want to know, perfect. So this means I give you a high factor or high weight to build my representation, and I will multiply your actual values with that weight. Or not the actual values, but like some other learned value. So those are just key, query, and value are just abstractions here. There are two types of attention, from decoder to encoder, and self-attention. So self-attention happens in the encoder and in the decoder, where you look at all the other words, and the encoder-decoder attention happens here, and they look at like the final layer, the final contextual representation of the encoder. When I say encoder, I mean like you have machine translation, so encoder is the source language, German, and then here you have English, and you want to translate to English, and this model here then produces English in the decoder side in a parallel way. So parallelization is important here because it makes stuff faster. We have a bit more time, so we could look at the results. They also make like a lot of ablation studies, and of course it was like trained by like, it was trained a lot with a lot of compute. And here they show transformer big. In blur scores you measure it, of course. Confinite. There's a confinite ensemble that's better, but ensemble is also like sort of cheating, or not the same sort of comparison, because ensemble means you have different models. And this is way simpler. Beam search is used, but I guess that's not so important. Here they have the big ablation study, or like studied different hyperparameters. They tested it on typical benchmark English to German, actually, and English to French. And since then, transformers became super important, and this is what a lot of stuff is based on, even in the multimodal space these days, or even just in the vision space. Okay, 40 minutes, 60 more minutes to go. This was actually before transformers, so I should have put that first. So before transformers, we have a paper published at ICLR, also about machine translation, neural machine translation by jointly learning to align and translate. Here, the main idea of the paper, I think, is summed up here. In this paper, we conjecture that the use of a fixed length vector is a bottleneck in improving the performance of the basic encoder-decoder architecture. What do they mean here? In the typical sort of LSTM encoder-decoder architecture, the encoder that processes the sort of source language, if you translate from German to English, that's German. The encoder gets the German sentence, blah, 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 German sentence is here, gets processed, it's several words, and then summarizes that into one vector. And back in the day, this one single vector was then given to the decoder, who then processed, was conditioned basically on this, and then produced like the English output, step by step, outputting it like in an RNN fashion. And they say this is stupid. Instead, the encoder should at each point be able to look at all the sort of representation of all the German words, and then weight them with a weighted sum, and then build some contextual representation, or some like weighted representation. They describe the typical architecture I described right now, the background, the neural architecture, the graphical illustration of the proposed model trying to generate the target word given a source sentence. Here's their learning to align and translate. So here you have the encoder, and it's a bidirectional LSTM, so it goes in this direction, that direction. Then I think it concatenates the both representations into like what they call a hidden state, or like a hidden, like something hidden. And then the decoder is allowed to, it produces those weights here, AT1, AT2, a time step T, that's the time step. Weights, with those weights, each representation of the source word is weighted and then summed up. And that's the input to our time step here. And here's the formula for getting those weights. And that's learned. that it is an alignment model which scores how well the inputs around position J and the outputs at position. This scores based on the R and N hidden state. So it's based on like the hidden state here. Hidden state S-1. This hidden state basically says, well, it's based on that one and says, hey, I need this kind of information. Or like, I want primarily those kind of words now. Yeah. Encoder bidirectional, like I mentioned. They also tested on this dataset, so I think that's the same one that the the transformer model tested on. Yeah. Here that's where I think those sort of attention visualization started, because you can now take the weights. So here, generated translation French. So here we have the generated translation. So at time step 1, it produces L, and we know that the row always has to sum up to 1. Time step 2 produces this, and we know that the row has to sum up to 1 again. And then we can see, of course, that we have those this pattern, because English and French are quite similar. So accord corresponds to agreement, and it attends to this. So this is sort of a good sanity check. If this wasn't the case, something would be wrong with the model. And here we have something interesting, that it breaks this pattern, because the attends to man, but also the L here has to attend to man as well, because it needs to know the gender, and that is it can't get that from the yeah. Okay. I'm already overdue. I guess then they conclude this was awesome. We have new state of the art, and it makes more sense to not encode it into a single vector. That's the key idea. Not encode the whole source sentence into a single vector. Okay. CompGuessWhat, a multitask evaluation framework for grounded language understanding. Here we are at language games again, so what we saw from David Schlangen, for example. And here, let's just look at the game shortly. The game is guessing. So you have two agents, and both can see the same picture. One agent has one object in his picture in mind. And I guess in this case it's a microwave, so one agent might have the microwave in mind here, and the other agent has to guess it. So it has to generate questions, and the other has to not generate stuff, and instead just do a binary decision or classification of yes and no. And there are also scene graphs involved. Yeah. So what's the contribution here? They produce and propose a new data set. I guess the big contribution is Crawler, an evaluation framework for grounded language learning with attributes with 3 subtasks. Goal-oriented object, attribute prediction evaluation, zero-shot evaluation. So new framework, a new data set. Including a semantic layer on top of the perceptual one. I think semantic layer is sort of like the typical relations you have in WordNet, so like part of, type of, etc. I read this paper at some point, but it's a long time ago. It feels like a long time ago. Evaluation framework. Evaluation framework for grounded language learning tests based on 3 different subtasks. Goal-oriented evaluation object. Okay, I think it's maybe easier in the short time to try to understand CompGuessWhat a bit more. It's an instance of our evaluation framework that's based on a guessing game. Okay, that's the guessing game I already described. It's based on gSCAN to promote the study of attribute-grounded language representation. The original gSCAN data is extended with a semantic layer on top of the perceptual ones. This layer consists of a collection of intentional and extensional attributes of the objects in a reference image. It is the visual genome scene graphs associated with gSCAN images with several attributes coming from the resources such as Visa and ImSitu. In order to determine the generalization power of the learned representation and the ability to be processed in all zero-shot learning set of reference games. This is interesting. So zero-shot set of reference games involving target objects belonging to an unseen object category. So what's the main idea here? The main idea is to extend a data set and sort of give an evaluation framework to evaluate agents that play that game and see what attributes they learn and whether they can do zero-shot evaluation, whether they can do zero-shot generalization. Then they also test models on it. Okay. This is hard to understand if you don't have time to understand it, I think. Grounded language learning evaluation. You propose the implementation of the quality. Found that the best performing model achieves a crawler score of 50. No, the biggest model's out of domain accuracy is under 30%. Out of domain accuracy, I guess that's a zero-shot performance. Clearly, even models with high in-domain gameplay success rates still have difficulty generalizing to new scenarios. Insights gained from the evaluation and new research directions for this test. Not able to accurately recover attribute representations. Models should be equipped with a co-grounding operator that fuses the textual and visual modalities. For instance, in the context of CompGuessWhat, it would be used to learn a representation for the current turn that is influenced both by both the language and the visual modality. Like, I don't know if they mean like something more than like the co-attention that you have in multimodal models or not. I'm not sure. The same framework could be applied to other multimodal tasks. So this is interesting. They say that you can use this framework also for image captioning. The goal-oriented evaluation would be the textual similarity matrix. The attribute prediction task. So you take the representation of the decoder here to predict the attributes in image captioning of the image. Okay, the time is over by 2.5 minutes almost. I need to take a short break to just drink a little. So I'll be right back. Let's see. Yeah, I'll be right back. I'll stop the recording for a second and then add the video. Okay, I took a little break and drank some water, opened the window, and now we can continue. This is quite hard, especially with papers that are like not just, you know, state of the art in some new way, but also introduce some general concept or new way to see things. I think that's hard to capture in 5 minutes, but let's continue. Okay, so here we have Vokenization from UNC Chapel Hill, improving language understanding with contextualized visual grounded supervision. So here the general idea, I have read this paper like a few months ago already. The idea is that you want to solve language-only tasks or have language-only data. And the idea is you take your language-only task, for example, you have this here, and you want to, for example, classify it or whatever, and you map like each token to some image. And this would be quite trivial if it was not contextual, so you could always map the word humans to some static image. Wait, my screen recording is saying stuff, but I think it's still recording, isn't it? It is, yeah, okay. But the idea is that the image that is shown here depends on the whole context. So if the sentence instead was humans are stupid, you might have a picture of a human here that looks stupid. That's the idea. And you get this, okay. The Vokenizer is what they call this sort of process or the model that learns this mapping from tokens to vokens, what they call vokens, and is trained on a relatively small image capturing dataset, and we then apply it to generate vokens. Okay. Yeah, visual supervised language models, vokens, visual tokens. Okay. Here it just says like how you could then basically use the typical way to, what the loss is basically. They say the typical loss in a language model like BERT looks like this. And then you can include a Voken here as well, I think. We convert the hidden output to probability distribution. Oh, I should also start the time again. Damn it, I forgot to set the time again. Now we have some time again, which is nice. So we have 2 more minutes. Plus it allows adding a token level classification task without modifying the model. Suppose the vokens come from a finite set. We convert. This is just about choosing which voken should be mapped to. And then it says like we can do it with BERT. There are 2 interesting things. They note generally like that has nothing actually to do with the paper itself, but just looking at the phenomenon that language is different when it is comes together with another modality. They say 2 interesting properties of multimodal data: smaller and simpler. So number 1, the language is smaller and uses maybe less diverse words. And often there are a lot of words that can't be grounded, like prepositions, or maybe prepositions can be grounded, but like the word and, it can't be grounded. They say the grounding ratio of English Wiki is 27%. Yeah, so this is interesting generally, I guess, to note. How did they train? I think I don't have the time to explain or look into how the token image matching model works. Oops. Oh no. Okay, that's it. I can't. Can I? Maybe I can go down. I don't know. But the time is already up. But the cool idea is like, or the cool thing, or the big challenge is how do we use multimodal representations but apply it to language only. Yeah. Okay, next one. Emergent communication pretraining for few-shot machine translation. The key idea is that for the first time they pre-train a neural network via emergent communication from referential games. Our key assumption is that grounding communication on images, as a crude approximation of real-world environments, inductively biases the model towards learning natural language. So the idea, the general goal is, or what they try to prove is, you can improve machine translation. They show this with blur scores, and they do it by pre-training via emergent communication. Emergent means that the language they use is not our natural language that we could understand. It's just some made-up language, maybe even way simpler than ours. Yeah, and they sort of, why is this useful? They say it's useful if you have very little data, and that if there's not even raw natural language data for a target language available. Yeah, and sort of this game that is played in the pre-training is, there's a speaker model that processes an image, so some CNN or like some maybe even pre-trained representation, and then has to produce a message from it. Like in this case, I think it's 16 tokens. And the listener then gets this message, processes it, and then has to do a classification between 255, I think in this case, images, and has to sort of, just based on this message, classify that it talks about this image here. And since the listener gets something, yeah, the listener then becomes the encoder and the speaker the decoder. But why is that? I'm not sure. I mean, I am sure if I think about it. I understood it at some point. Decoder. The decoder gets an image and has to produce language. It gets language and has to produce something. Yeah, okay. But yeah, that's the idea. You take, oops, what happened? You take those weights here and then initialize the decoder and encoder instead of random weights. You initialize it with weights from the listener and speaker. Then he talks about like related work. A lot of emergent communication work has been done before, like generally sort of throwing your agents into an environment and having them together solve some task, and they need to communicate about that in some like sequence of tokens. For me, it always feels like those sort of emergent communication things always makes me question what is actually language, at what point is it language, and at what point just some sort of flat sequence. Yeah, they talk about that this might give a good inductive bias, I guess. They use GRUs for the speaker and the listener as well, and the listener then has to do some classification. Given the message M and any image I, we define a compatibility score. And the score, like you give score to 255 images based on the message, and then the high score is your classification. So the source to target translation model consists of listener S and speaker T. So the listener gets input emergent language domain, output image domain, and the speaker gets image domain, output emergent language. And in between sort of there's this image domain, so that the listener is the encoder, and the speaker is the decoder, because sort of then the input and the output are emergent language communication. And you can input emergent language domain, output image, output that image into that, and then get emergent language domain. And since in machine translation you don't have an image domain, they also say we need an adapter module, which sort of adapts this, like, sort of that's a step in between the image domain and this image domain for language. But that's a bit vague for me. They also have some technique called annealing, which is about preventing the parameters from drifting away from the initialization W star. And then they have some before. Okay, the time is now almost over. They show that with like very few samples. So here you see like the setup where it's useful when you have very few samples. And then you see if you use the emergent communication stuff, it gets up from like 4 to 8, 5 to 10 on different languages. And that's what they show. Okay, the next paper, executing instruction in situated collaborative interaction. So we again at language games in some environment, and again 2 agents that have to communicate. That's the idea, they have to communicate in some environment, which looks like this. That is the view one agent has. It's from Cornell and a bunch of other people, collaborators, and you need a lot of collaborators here because this is like about game design sort of, and more than just language or vision. Okay. The game, by the way, they play before I am too silent for too long is they play a game called Set, where you have to like, and they play together and they have to collect cards together that have certain properties. So only some number of 3 cards together make a winning set, and some others do not. And there's the agents are not equal. One of them sees, I think, where is it defined? Where not only but also, I think one of them sees the whole board. I'm not sure, and the other only the leader's view. Yeah, the leader sees the whole board, and the follower only a small part. So the leader tries to make up a strategy, and like a long-term strategy, so that they most efficiently get the most cards in the smallest amount of steps. And the follower, has to follow those instructions. So has to like sort of understand what the language means, and like, okay, the tree refers to this and that. Yeah. And they also describe some problems. For example, I think one is recovery from cascading errors. And also they introduce explicit reasoning about instructions when you have multiple goals in mind. I'm not sure if there's like one simple. This is their network. It's not very easy to understand just from this. But in the end, of course, we can look here. The follower has to generate actions like through an RNN here, and it has to turn left and right. So I guess the actions space is like maybe 4 actions it can take. And the leader has to make a plan here. But this is hard to do in like 5 minutes now. So let's more or less jump to the conclusion. Here they evaluate those cascaded errors, I guess, in a long fashion. Discussion. Here. On human evaluation, highlights several directions for so they evaluated with humans, like how they got also annotations from humans, I think a lot. While human leaders adapt to the agent, scoring up to 14 points. So human leaders can adapt to the agents, but it's still better to have a human follower. An important direction of future work is the removal of... Okay, they want to remove the full observability assumption for the leader, I guess. Other future directions include experimenting with using the interaction history, expanding the learning example aggregation to error case beyond. Oh yeah, the thing they propose also is called serial bar. This environment or this like test of agents, this testbed. So they say this is also useful to study pragmatics, which is the idea that language is like more than just sentence-based, but like about what you want to achieve and stuff. Okay, and they also say this is unidirectional, so there's just one-way communication. Okay, I must say I'm quite tired at this point, but let's keep going. This is the point of a challenge. I'm also a little bit behind with the time. Maybe let's try to do a different strategy to read the abstract because I haven't read this really before. So here we have to read the abstract in detail. Recent work has shown that large text-based neural language models acquire surprising properties for one-shot learning. So one-shot learning is you get one example, and from that you have to like generalize. So basically I think here they mean GPT-3, because with GPT-3 you basically give a prompt giving one example and then it generalizes. Here we show that an agent is situated in a simulated 3D world and endowed with a novel dual encoding external memory. So there's memory. I think I haven't read a lot of papers where memory is like discussed, so this might be interesting to read at some point. And then they say such models that are endowed with like novel dual coding external memory in a 3D world can exhibit similar one-shot word learning when trained with conventional RL algorithms. So you're not trained with the typical language modeling thing, but with RL. After a single introduction to a novel object via visual perception and the language, this is a DAX. So this is a very typical setup you would have for children. You point at something and say this is a DAX. And it's a novel object. The agent can manipulate the object as instructed. Put the DAX on the bed. Okay, so that means after seeing it once, it has already like adapted its weights to know what that means. Combining short-term within episode knowledge of the nonsense word with long-term lexical motor knowledge. There's one-shot word object by to know example in the same ShapeNet category. So they use apparently some ShapeNet, which is maybe like WordNet, but more about like geometry of stuff. And they say like you can then effective in setting with unfamiliar numbers of objects. So maybe if you have then like plural of DAXs, I guess. Intrinsic motivation, simulating the agent to seek names for objects that may be useful later. Okay, so intrinsic motivation in this case means having a motivation to learn new names and new words. Together, the results demonstrate that deep neural networks can exploit meta-learning, episodic memory, and an explicitly multimodal environment to fast mapping. Again, a lot of cognitive science, I feel like. Okay, I have 1.5 more minutes. So this is how the environment looks like. It's a simple room with some simple objects. Yeah. Pick up a plicket. Okay, it's built with Unity game engine. I think a lot of stuff as I saw from now on so far is built with Unity. A room contains a pre-specified number n of everyday 3D rendered objects. So I guess you see 5 objects, one of them is DAX, and you have to know which one it is. Okay, so the agent is allowed to do two things: discover, go around, I guess, like look at stuff in different angles. I don't know if it can touch stuff or like move stuff. And the structure phase. It must explore the room and fix it on each of the object in turn. When it's fixed on the environment, returns a string with the name of the object. Okay, during the discovery phase, it already gets words. The precision of all the object the edge will be randomized. And then it gets shuffled again, so that it can't just remember where it was. So everything gets shuffled. And then you have to pick up that object. Okay, and you have to hold it up. I don't know if that's relevant that you hold it up for like a longer time, but okay. Okay, let's jump to the conclusions. Cool pictures, more cool pictures. Conclusion. I have highlighted various benefits of having an explicitly multimodal episodic memory. So I guess this paper is a lot about memory, episodic memory, like remembering things when you just heard them once. Query its memory in a modality-specific way, either within or across modalities, sort of knowing like I have to remember something and it was a visual, or I have to remember something and it was a word, or I heard something. To realize fast mapping, a notable aspect of human learning. Is fast mapping just one-shot learning, or is fast mapping more than that? Okay, transformer-based memories. Okay, I didn't know there were transformer-based memories. Third, in case where it is useful to estimate the degree of novelty or surprise. Okay, a lot of cogs are here again. Oh god, I'm so overdue. In order to save a bit of time, because I want to stick to my 100-minute, I will try to make this one shorter. Again, we have a benchmark based on some like game environment or like something similar. So here it is about composition, and it says that we can interpret stuff where we know the individual parts but not the whole thing yet, but we can add it together. Read the pink Brontosaurus by the Ferris wheel. So we know what a pink Brontosaurus is. Neural networks struggle to interpret novel compositions. gSCAN is a benchmark for evaluating compositional generalization in situated language understanding. Situated because it's some 2D environment, I think, in this case. Going beyond a related benchmark is focused on syntactic aspects. Yeah, it's data for grid world, facilitating novel evaluations for acquiring linguistic motivated rules. Okay, this is one thing agents apparently have to learn. For example, agents must understand how adjectives such as small are interpreted relative to the current world state, or how adverbs such as cautiously combine with new verbs. So they have to understand that small is something relative to something else. We test a strong multimodal baseline model and a state-of-the-art compositional model, finding that in most cases they fail dramatically when generalization because systematic compositional rules. Okay. I have 2 more minutes because I try to save time. So that's the thing. Command walk to the red small circle cautiously. I think cautiously just means that you look left and right here. It has to turn, has to go, and then there. Yeah. The red small circle has different reference and demands different action sequences. Being cautious means looking both ways before each step. So this is sort of about program generation, like some high-level instruction, some very simple program, like some loops also, right? You have some loops here, I guess, like each time you have to look left and right and stuff. Okay, 1 more minute. How does the related work look like? Yeah, there was scan, so it's based on scan. I think the new thing is grounded and not just about syntactic composition, but also about like relevant to some environment composition. That's the baseline. No time to understand it here. Conclusion. The scan benchmark has catalyzed new methods for compositional learning. They say here that scan, that their new sort of findings here show that models or results are just exploited artifacts in scan that are not central to the nature of compositional generalization. So scan was flawed. gSCAN removes these artifacts by introducing more sophisticated semantics through grounding. So apparently this makes it harder to sort of exploit artifacts. And most models fail. So this is a good sign. That means like good models were unable to find any artifacts. In future work, we plan to extend gSCAN to support in reinforcement learning, although certain splits are not straightforward to translate, pushing, spinning. Okay, I don't know what. Okay, I can't judge why RL is hard for that. The benchmark seems demanding enough with supervision without adding RL sample complexity issues. RL seems unlikely to improve future learning or target identity, but it may help with length. Okay, I'm over time, but this sounds interesting. Oh boy, this is a huge paper. Okay, we will not cover that. This is a long list of authors, like I think 20 or 30. Interactive agents, groups, imitating interactive intelligence. Here we study how to design artificial agents that can interact naturally with humans using the simplification of a virtual environment. To build agents that can robustly interact with humans, we would ideally train them while they interact with humans. However, this is impractical. We approximate the role of the human with another learned agent. Use ideas from inverse reinforcement learning. Interesting. I don't know what that is. To reduce the disparities between human, and agent interactive behavior. So they try to like get rid of the problems coming from that it's actually not humans. So they say it's quite hard to evaluate what they did. So including evaluation by humans who watch videos of agents and interact with them directly. Our interactive speed. We interact with the physical world with one another. We often to build artificial capable of human language. But also with how humans behave as physical agents in the world and as communicative agents in groups. So it's not enough to just think about or like research how humans think in the abstract, sort of like looking at like reference resolution or stuff like that. You have to look at the physical world and communicative agents, they say. This work initiates a research program whose goal is to build embodied artificial agents. So this seems like a start of some bigger thing at DeepMind, maybe. Where it can perceive and manipulate the world, understand the process to produce language and react, and given general requests, such a holistic problems concept. Okay, 2 more minutes. This looks similar to the paper before from like language learning fast and slow, but it seems a bit more complex. Yeah. So they didn't even mention yet what the main sort of, it's just a long list of like experiments and sort of like describing the environment. So I would say, let's go to the bottom. This is a huge paper. Okay. Conclusion. In this work, we sought to build embodied to interact with their world, with each other, and with us. So I guess this is cool. It's not just saying like we got state of the art or we got a new data set. It's just saying we did a lot of experimentation. And it's a big project, I guess. So there's nothing like fundamentally new. It's just like studying and doing this in detail and a lot, like with different models and like with all things involved, communication, manipulation, everything. And we are capable of giving. Also, self-supervised undertook tasks without easily programmed. Why the agent's behavior were not perfect. Okay, seem to. Okay, this sentence sounds sort of interesting. If the agents introduced into human environments are not reasonably capable from the start, we believe there will be little incentive to engage with them. Sort of, we get bored if you have to teach them like a million times. And there they say like here the agents are interesting enough, quite subjective I guess, maybe interesting enough to entertain continued interaction. By at least showing signs of learning at each step. Okay, I will drink a little bit, and the next paper is then probing multimodal. Oh, this is hard. This is a hard challenge actually. Where's my water? Okay. From Sweden, pretty cool. Some university I haven't seen so much. Probing multimodal embeddings for linguistic properties, the visual semantics case. So probing is a typical way to sort of see in pure language models like what the model has actually learned. Well, the power of it maybe comes from the distillation. It's about understanding inner workings, and that they're poorly understood. And they take the notion of probing. Probing is usually taking like the representation on top of like bird and doing a simple classification task maybe on it. Define the here, okay. Motivation, the probing task proposed by Kuno. Probe sentence embeddings and are categorized according to the type of linguistic properties they capture. Surface, syntactic, and semantic. So you have probes for each of those. Surface information comprises probing for sentence length and the word content, whether the sentence contains a given word. So I guess you would, for example, take one word, like you have bird, and it processes like a bunch of words and give you contextualized embeddings. You would probe one of them maybe and ask like, what is the length of the sentence? Is it 4 or 3? Or you could ask like, in the semantic case, the probing in the syntactic diagram shift tree depth, like you could ask like, what is the tree depth? This is quite tricky, I think. So this is sort of linguistic probes. Or semantic, semantic odd-man outing, the probing task that probe for semantic out tense, subject and object number, semantic odd-man out, and coordination inversion. The tense task consists in finding the tense of the main verb, binary classification, or like future, past, or present. Okay, so this is like seeing whether the model has learned some linguistics that we as humans normally study, or is it just something completely else that the model has learned in order to solve the task. That's the idea of probing. And then you can do it for multimodal embeddings. A general view of visual semantic probing tasks and live the idea of in the multimodal realm. In the visual semantic, such a property may be the embedding associates visual properties which are now in the text component. Or the embeddings encode the number of objects in the image. The embeddings encode, this is one thing they might probe, like the number of objects in the image. It's usually the classification task. Direct probing. Our first proposed probing tasks are instances of direct probing as discussed in Data. The task is to determine which of the 80 MS COCO objects categories are present in a given image. We restrict the dataset to image capture transmission only. Where do they come from, the embeddings? I don't know, okay. Semantic congruence. Dataset, we use the micro. The visual semantic models used for our programming task are those. In addition, we use the well-known unimodal language models BERT. As a benchmark, they use BERT. They get the stuff out, and then I guess the multimodal models were trained, for example, on image captioning. So I don't get like if it's trained on image captioning, but I also don't have time to question this. Yeah, okay. I guess it's fine. Probing. For example, if the head is walk in the abstract category verb motion, then we might choose fly from the same category. To explore a range of linguistic features for the nouns. Okay, I guess the only thing we can say is that they, for example, did direct probing now. And they also probe for the number of objects, results for the number of objects. And I'm already quite overdue with my time. Oh, it's sad, because this paper I think is also interesting, but I'm so tired now. A recursive mental model for dialogue navigation. I've looked at this paper before, and I think the cool part is this recursive refers to that the one agent tries to model what the other agent sort of tries to reason. If I would say this, what would the other agent then say? And then sort of think like, should I based on this, should I actually say it or not? It's about dialogue navigation. They say apparently the much existent work focuses only on the latter. So ask human questions and understand answers. And they mostly focusing on like understanding the answer that comes from a human, but not so much about like what questions are reasonable to ask. Two agents where one agent navigates and asks questions that a second guided agent answers. The cool part is the theory of mind part. The navigating agent, so the agent that actually has to go around, models the agent that gives instructions, so the guiding agent, to simulate answers given candidate-generated questions. So if I'm the one walking around, I would think like, okay, I have a problem. If I ask this question, would the other person say an answer that helps my problem? They use reinforcement learning, and the reward signal is the progress they make towards some goal. Like here, the red dot is, I guess, the goal. Yeah. Interlocutor modeling may be a way forward for human where robots need both. Okay. Okay, so this is pretty cool. I like theory of mind, but I haven't done too much. I guess I like too much stuff. Yeah, we have only a little bit more than 1 more minute. Let's look at the conclusions. We present a 2-agent parallel. So one novel thing is that it's like about question generation and understanding answers, and not just about understanding answers. Single-verse in vision language navigation is largely limited to navigation only. Some have limited additional instructions. By contrast, this work requires navigation. Question answering components for learned end-to-end dialogue. We find that simple speaker models are insufficient for the dialogue setting, and demonstrate promising results from a recursive RL formulation, with turn-taking informed by theory of mind. I wonder how sophisticated like the theory of mind here actually is, or if it's quite simple. There are several limitations to the model presented in this paper. We consider the only agent model determined. So there's no human involved. That's a bad thing, sort of, they say. And they say like if you have an actual human, that has to be explicitly modeled. So you shouldn't just assume a human is like a copy of you in this case. Yeah, this is interesting because this could model like typical psychology research maybe. Additionally, we currently require the navigator agent to ask questions after a fixed number of steps while determining when to ask questions is a complex problem in itself. This is also interesting, yeah. So sort of knowing when to ask question here is just given, like now ask a question after 5 steps and now again. Yeah. So here we have theory of mind, we have like question asking and answering and understanding the answer and not just one thing. Okay, we are almost done. Self-supervised learning through the eyes of a child. This is pretty cool. This is about modeling how children learn stuff, like actual children, not AI children. How much of this early can be explained through generic learning mechanisms? So the question is like if you have all the information that a child has, so all the input, how much can you do with all that input with current deep learning architectures? And this sort of also tries to answer then, given depending on what results we get, this must help us understand how much innate inductive biases a children has. Addressing this fundamental question is currently not feasible, because you have had to model like a lot of stuff about the child, but we can make like small progress. But in more narrowly defined domains, such as the development of high-level visual categories. So it's about what the child sees and how it builds high-level visual categories from that. So self-supervised learning, there's no supervision, it's just sort of finding features that are useful maybe to predict the next frame or something. And it's based on one very cool video data set, where one from the perspective of 3 young children. So each children had a camera on the head and everything was filmed for a few years, or maybe a few months. Development psychology. Is it about predicting the next frame? Dataset, SACAM is the dataset. I really hope to work with such a dataset at some point. Train models on the HACAM without using it. We develop a new self-supervised learning objective based on the principle of temporal invariance. This objective is based on the observation that higher level variables in a visual scene change on a slower time scale than lower level variables. Hence, a model that learns to be invariant to changes on fast time scales may learn useful high level features. So the idea is that in like a few frames, the high level, like in your convolutional neural network, the high level feature of there's a cat in the picture. If one like high level feature is cat, this shouldn't change. This should only change like after 20 frames when the cat is out of the picture. So that's the idea for self-supervision, that you have some high level features that do not change in the next frame, and if that does happen, you penalize it, I guess, with a loss function. We implement this idea with a standard classification setup by dividing the entire video data into a finite number of temporal classes or episode of equal duration. Okay, the objective then is to simply predict which episode any given frame belongs to. Okay, this is actually quite simple to understand the objective. Like you have like a really long sequence, what the child sees, you divide it into equally big chunks, and then for part of the chunks you say, are you part of that chunk or not? Or like not, are you not part of the chunk or not, or like in what chunk are you part of, like and then you can classify into 1,000 classes or something. Yeah. And apparently it's psychologically plausible, they say. Hippocampus. So this is pretty cool to learn a bit about the neuroscience and cognitive science part. Let's jump to the conclusions. I must say I'm quite happy if this is done soon, but this paper is also really cool, so I'm torn between being super tired and happy to read such cool work. In this work, we took a first step towards rigorously addressing a fundamental nature versus nurture question. So how much innate biases do we have? Can we, like, with general purpose architectures, can we learn a lot of stuff, or do we need to hardcode more? By applying modern self-supervised learning to restrict subtypes of visual level, we demonstrate the emergence of powerful high-level visual representations. Our analysis suggests that although these representations do not strictly correspond to abstract categories, they are abstract enough to support high-accuracy, non-trivial downstream categorization tasks, invariance to natural transformation, and generalization to unseen category exemplars. So they used those high-level features maybe to do some downstream categorization, like is there a dog or a cat in the image, maybe. Do not strictly correspond to abstract categories. I guess there they looked like does something correlate with, like some single feature correlate with dogness or catness, I don't know. It still remains open how far we can push the negative learning algorithms to even larger and richer. Because this was ICLR, or I think NeurIPS, you had to do a broader impact. So I will extend the time a bit because I've never read a broader impact before, or maybe some, but not like some randomly picked one. These visual as a basic scientific, what kind of visual ability can be learned from development realistic work? They say so it does not have foreseeable societal consequences because it's basically fundamental science. To the best of our they say like the data set was approved and that's it. Okay, nothing exciting. Okay, one more thing about like children learning. The last one, Visuospatial, that's a funny word, Visuospatial Dataset for Naturalistic Verb Learning. Brown University. It's a simple paper introducing dataset. Our data is collected within a virtual reality environment is designed to emulate the quality of language data to which a pre-verbal child is likely to have access. Pre-verbal child is one that doesn't understand language. Naturalistic spontaneous speech paired with richly super-grounded visual context. So this means spontaneous means it's not targeted at the child, but might just be like a lot of like random stuff. Our results are consistent with evidence from child language acquisition that emphasize the difficulty of learning verbs from naive distributional data. I don't know what naive distribution data is. We discuss avenues for future work on cognitively inspired grounded language learning and release our corpus with the intent of facilitating research on the topic. We make two main contributions. First, using a virtual reality kitchen environment, we collect and release the new Brown corpus. 18,000 words of spontaneous speech alongside rich visual and spatial information about the context in which the language occurs. Our protocols, I guess the protocols mean like the protocol that was given to annotators or to people who helped this thing. So yeah. Second, we use our corpus to compare several distributional semantic models. What is a distributional semantic model? I don't know. Not directly. I mean, I sort of know what distribution means, but yeah. Specifically comparing models which represent the environment in terms of objects and their physics to model. They focus on verbs, so that's the main thing. Yeah, I feel like nouns are often like way more focused on, like for example, the CompGuessWhat we saw was like focused on guessing nouns, and yeah. More so than nouns, verb learning is believed to rely on subtle combination of both syntactic and grounded contextual signals. And verb learning, I would say, is even like connected to videos or not images, right? Is it images here or videos? Okay, they find that strong baseline models perform only marginally above giants. However, I guess it's a classification problem. I don't know what it is. However, comparing models reveals intuitive differences. Screenshots of a person picking up a banana in each of our two kitchen aesthetics. Okay, so it is videos, right? Data recording. Okay, yeah, it is videos. Okay, sorry. Comparison to child director speech, vocabulary distribution. It's also about the spatial stuff. So it's not just about pixels. There's more like because it's like based on some game engine maybe or some other environment. You also get like the actual spatial information. Okay, now they have a lot of linguistic analyses of like different part of speeches and simple words. Models, context encoders, object-based. Intended to feature engineered approach. So this is very linguistic. This is interesting to broaden my mind later on. Pre-trained CNN for the visual features. Okay, this is very old school. This is cool. Dimensionality reduction. Evaluation. They talk about like vague actions. That it's okay. Okay. Conclusion. We introduced the new brown corpus, so this is the main contribution. I'm a little bit overdue with time. It was in some environment, some kitchen environment there, was collected. Show that compared to existing corpora, the distribution of vocabulary collected. So they say like that the language use is more realistic regarding like what children normally hear, what children normally hear. And they use like, compared to like other papers, more like traditional linguistic models, like distributional models. Okay, this was my challenge. This was hard. My mouth is quite dry from like talking 100 minutes and I need to get some water and my brain is quite mush. But I took something away, like I feel like I learned, I don't know if I learned to scan so quickly, but through talking I learned to get the main points. For example, from the recursive mental model paper, I still remember that like most papers before that only focused on understanding answers, but not on how to ask questions. And I still remember from this paper, through the eyes of a child, that their task was to predict simply in what sort of in what episode some frame was part of. Okay, I'm talking quite chaotically right now, but what I'm saying is I remember more and I was better at getting the gist sort of by being pressured to quickly find it. But I feel like sometimes I should give myself more time because I had to, like there were some questions that I really wanted to get answered, but I had to move on. So I might adjust the challenge at some point because 5 minutes is really small. It's barely enough to like read the abstract, especially if you have to think about talking to others or like presenting it to someone, some imaginary listener. Yeah. I think once, like in 10 years, when I'm some expert researcher, I could get the main idea by reading the abstract because I can sort of infer from the abstract what they probably did. But for now, I might still have to read the papers more in detail. Thanks for sticking with me until the end. I think most probably didn't. I barely stuck with me